Hi, I'm Dave Parrish, and together with my colleague Jennifer Folcard, we'll be demonstrating some of the problems and solutions in achieving net zero on the UK electricity system. So this is a representation of the UK electricity system. We have all the regions of Britain here. We have Cornwall, we have England, Scotland and Wales, and in the middle here we have the Midlands, if you like, and over in the far side here we have Ireland, so not UK, as part of the EU. And this representation is all about demonstrating the role of flexibility in giving the system operator proper control of the system to maintain it in a healthy condition. So we're using a pumped water system where water in the tubes on the tables and in these manometer tubes represents energy in the system and the health of the system. And we have a tolerance band here where the system has to be kept between the lower and upper limit. That's the responsibility of the system controller to make sure the system stays healthy. As we've been closing down fossil fuel power stations, we've been taking away some of the control mechanisms that the system operator uses. So as we increase the amount of renewable energy that we need on the system, in line with our decarbonisation goals, we make it more difficult to control the system. So this model is designed to demonstrate that difficulty in control and what's needed in terms of flexibility to achieve that control. The model has base generation and base load in this central table. So this represents the minimal load that the UK has, which is operating all the time, and the base generation matches that load and is typically created by nuclear in the UK. In the regions we have renewables, here's solar, we have demand, which is residential here, and we have a peaking plant here, which is a gas-fueled generator, which is designed specifically to run for only a few hundred hours a year to meet critical needs on the system. We also have a factory here in Scotland. We have wind in Scotland. We have an industrial freezer in Wales. And we have some energy storage here, which could be battery or could be pumped hydro storage. And we have an interconnector, a European interconnector, in this case going across to Ireland. And the model demonstrates the balance or the imbalance. If the wind blows particularly strongly, we'll see a response in the manometer. And conversely, if we have a lot of load, we see it dip. So what we use the model for is to demonstrate that we need to achieve balance on the UK electricity system, and we need to achieve that balance on a second-by-second basis. If we fail to achieve that balance, the system goes out of control with critical consequences. We're going to go through a day in the life of the UK system here, and we're going to start off in Cornwall. And you'll see at the moment that the system is perfectly balanced. Let's say it's 5 o'clock in the morning. We've got base load operating and base generation covering that. And all of the regions are identical. Let's make the assumption that Cornwall wakes up earliest, and as Cornwall wakes up, the residential loads come onto the system. People getting up and putting kettles on and taking electric showers and turning lights on. And you'll see as we put that load on the system, we're taking energy off the system, and at the moment it hasn't been matched by generation going on. So we're now gone out of limit and we've got a critical situation on the system. So we've got some solar generation here, but it's too early, so we haven't got any solar operating. The wind isn't blowing in Scotland at the moment, and we need to take some other action. So in this scenario, we have a peaking plant here, which is one of these gas-fired peaker plants, which is designed specifically to run for a few hundred hours a year in exactly this sort of situation to make up a shortfall as and when it occurs. So the peaking plant is now operating and bringing that system back in control, and you'll see that all of the system comes up together with Cornwall. There's a slight delay. So we're happy now, system's okay. January is going to come across, and now England is waking up as well. So we have some residential load occurring in England. So again, the system starts diving, and again going out of control. You see England is low already, Cornwall is low, and the national system is out of specification as well. So again, we have to take some action, and that action still very early in the morning, still no solar PV, still no wind. That action is to task another peaker plant at the moment. So we're burning fossil fuel gas in those peaker plants, which we don't want to do any more than we absolutely have to. So as soon as we can turn them off, we will. So what happens now is, let's assume the wind starts picking up in Scotland, and we have some wind energy coming onto the system. And you'll see now we've gone the other way. We have too much energy on the system. Our system is out of specification on the high side. So clearly we don't want to be burning that fossil fuel anymore. So we'll close off the second peaker plant first, and then if we can, we'll close the second one as well. It doesn't look like we can at the moment, so we'll leave that as it is. So the other thing that's happening now is that this factory is about to open. So the workers arrive at the factory, and the factory load comes onto the system. And again, that load is taking energy off the system, and it needs to be met by some generation to balance it. So we've got one peaker plant still operating. We have some energy stored here. With the rationale is that we use the fossil fuel peaker plants as little as we can, and the renewable energy as much as we can, to achieve our decarbonisation. So we have some stored renewable energy in our energy store here, which could be a battery, it could be some other mechanisms. So Jenna is going to bring some energy from that system into play. And as she does that, the system recovers. So we're coping again at the moment. And as we're doing that, the system is now coming high. So we may choose to turn off the peaker plant we had running. Which is in Cornwall. Now, the battery here has a finite storage capacity, and we're now reaching the limit of that capacity. And as we do so, you see the system is now dropping. So we've depleted the energy store, so that's no longer an option. So we now need another solution. It's still not that windy in Scotland. There's still not much sun in Cornwall. Let's assume the sun is beginning to come out, but only a little bit. So we have some solar generation, but not enough to recover the system. We have another flexibility action where we can buy energy from Ireland over the EU interconnector. So in this case, it is windy in Ireland, and the market rate for buying that energy is reasonably good. So we're going to buy some energy from Ireland. So we bring that energy in from the EU, and that corrects the system. What we have now is in Scotland, the wind is coming up, increasing. Again, it's renewable. We don't have control of it other than turning it off. We don't want to turn it off because it has a huge value to us. It's also getting a little bit more sunny in Cornwall. So we have quite a lot of generation coming onto the system now, and we're still buying from Ireland. So certainly now we don't want to buy from Ireland anymore. So when that contract ends, we won't replace it. So we stop importing from the EU, and the system comes back into specification. At this point, it's getting even windier in Scotland, and even brighter sunshine in Cornwall. And again, we're out of specification now. So we have another action that we can take, which is called DSR, which stands for demand side response. So we have a large industrial freezer here, and this freezer, let's assume it contains meat, and that meat is held at, let's say, minus 18 degrees C. And they can subcool that meat to minus 24 with no harm to the product at all. And there's a market value in them providing that service. So it's called demand side response, and this freezer center is now going to subcool its freezer. It's technically called cryogenic energy storage. And later that temperature will be allowed to rise back up to minus 18, so there's no wasted energy at all. So they're now soaking up the abundance of renewable energy which is on the system. Again, this is a finite energy storage mechanism, so they can only do that for a certain amount of time. And let's say we're running out of that time now. So we can no longer subcool the meat. It's as cold as it's allowed to be. And simultaneously, we've got even more wind on the system. And at the same time, because it's now middle of the day, the residential loads are diminishing because people have gone to work. A lot of homes are empty. So here we have a situation where we're out of control. We've got too much generation, not enough load in Cornwall. Similarly in Scotland, and that's affecting Wales and England as well. What we do now with too much energy on the system and an empty storage is we will now send energy into storage. We want to leave the renewables operating absolutely as much as we can. That's our low carbon or zero carbon energy. So we have to make a manual intervention here to reduce the height of that, and Jenna will now send that energy to store, which brings the system back in control. Okay, so we're controlling the system and simultaneously putting energy into store to use later on when we want it in the opposite direction. We'll assume now that the energy is, the store is full. Again, it's a finite resource. So like others we've discussed, it can only happen for a certain amount of time. So the energy store is now full, and we still have a large amount of wind power on the system, a large amount of solar power on the system, small residential loads because it's the middle of the day, industrial loads are operating, and we have too much energy on the system still. So what this is demonstrating is that we need more mechanisms for storage, we need more mechanisms for DSR, so demand side response, more ways of leaving the renewables operating and storing or using that energy at a different time of day. So all of those are bundled up and termed flexibility. So those flexibility actions need to be manifold right across the regions, giving the system operator all of those choices to make at any time. If we're going to achieve our target of net zero by 2050, we're going to have to increase the amount of renewable energy on the electrical system hugely. Currently we have a little over 30% of the energy on the system is renewable, the rest of it being fossil fuel based or nuclear. That figure will have to increase substantially, so more than double what it is now. And whilst doing that, we're taking control away from the system operator in that they can't control in the same way the renewable energy assets in the same way that they do the large power stations. So this means that to achieve that decarbonisation, we need to have flexibility throughout the system, both in terms of loads and storage and generation. And that flexibility will be controlled under markets, devised and operated by the system controller to benefit the whole UK electricity system.